Every bedside patient monitor beeping out a heart rate in a hospital today descends directly from a piece of hardware built for one job: keeping an astronaut's heart beating during a 1965 spacewalk. An astronaut spending 6 months on the International Space Station loses bone density at a rate that exceeds the most severe clinical cases of osteoporosis doctors ever see on Earth. And in 2019, one identical twin came back from a year in orbit with chromosome caps that had somehow grown longer in space before rapidly unraveling the moment he touched down. NASA never set out to advance terrestrial medicine. These breakthroughs are the accidental byproduct of a single, highly constrained engineering problem: trying to keep a fragile human body alive in an environment where it was never built to survive. If we put you in orbit right now, your body immediately enters a state of biological crisis. Stripped of gravity, bathed in cosmic radiation, and subjected to total isolation, your physiological wear and tear accelerates, compressing decades of aging into mere months. By tracking this intense survival challenge in a tiny, highly monitored population, the space agency inadvertently constructed a highly controlled medical laboratory. During the early Mercury program in 1958, physicians faced a strict engineering constraint. There was no established technology to continuously measure a person's heart rate, breathing, and temperature from a distance. A contractor named Space Labs Medical was founded specifically to solve this. They shrank vital sign sensors down far enough that astronauts Edward White and James McDivitt could wear them comfortably outside the spacecraft during America's first spacewalk in June 1965. The underlying challenge of shrinking heart rate sensors and transmitting that data reliably over a distance is the exact problem every modern hospital ward and ambulance has to solve. The same corporate lineage that built the wireless telemetry for that 1965 spacewalk remains a major supplier of the patient monitors used in hospitals globally today. This diagram shows the mechanical consequence of microgravity on the human skeleton. Without the constant weight-bearing load of gravity, the cells responsible for breaking down old bone tissue quickly outpace the cells trying to build new bone. Looking at the resulting drop-off, astronauts lose 1 to 1.5% of their bone mineral density per month. A single 6-month mission strips away as much bone as a postmenopausal woman on Earth loses in an entire year. No ethics board would ever allow doctors to induce this level of accelerated bone destruction in a healthy patient. Spaceflight offers an incredibly efficient, natural laboratory to observe the condition. To combat the loss, NASA runs direct trials. Astronauts strap into vacuum cylinder rigs to perform heavy-loaded squats and deadlifts against simulated weight, while researchers test anti-resorptive osteoporosis medications directly in orbit. The data generated by trying to protect the skeletons of astronauts is feeding straight back into treatment protocols for elderly and immobilized patients down here. In 2015, NASA got an experimental opportunity impossible to replicate in an ordinary clinic. Astronaut Scott Kelly spent 340 consecutive days on the International Space Station, while his identical twin brother, Mark, stayed on Earth as a genetically matched control subject. 10 different research teams tracked their gene expression, gut microbiomes, and cognitive processing before, during, and after the mission. This animation illustrates what happened to Scott's telomeres, the protective caps on the ends of chromosomes that typically shorten as we age. During his time in orbit, Scott's telomeres measurably lengthened. But within days of his return to Earth, those lengthened caps rapidly unraveled, leaving him with more critically short telomeres than before the mission even began. This was a sample size of one pair of twins, and the data showed that roughly 91% of Scott's genetic expression changes safely reverted to normal within 6 months of landing. By compressing a slow biological process into a fast, observable timeline, spaceflight handed geneticists a new set of data points regarding how human DNA reacts to extreme stress. Consumer wearables that measure heart rate variability today evolved from cognitive stress sensors built for astronauts, and space station drug trials continue to shape bone loss clinics. The genomic tracking refined during the twin study is actively dictating how doctors will monitor crews on multi-year missions to Mars. Space medicine functions by solving extreme, tightly controlled biological problems that do not yet exist anywhere else on Earth, until eventually they do. From a 1958 telemetry contract to a 2019 cover story in Science, the body never asked to go to space, and medicine is still learning from what happened when it did. January Science tells the story behind the science, one disease at a time. Subscribe for the next one.